go. Okay, so ladies and gentlemen, I'd like you to go to the model. You should have something like this, except you will see that I've added something called initial count infective, which we'll be manipulating. So this is going to allow us to change the number of people that start infective. And I'd like you to add it to the model. What you do to do that is you go to the System Dynamics area, go to Parameters, drag down initial count infective. Its default value will be 470. And then for susceptible and infective, we're going to modify the initial state to depend on this. For susceptible, the initial value will be 200,000 minus this value. And for infective, the initial value will be initial count infective. What am I doing by those changes? Anyone? Why am I subtracting it off here, 200,000 minus this, whereas this one, it's just the value of this variable? What am I keeping constant?
The total population.
Total population. I don't want to skew things by having more people start infective that we're going to have more people in the whole population. I want to keep constant the total population. Very common in this sort of modeling to want to make sure that a change really only affects one thing at a time. Here my interest is affecting what fractions start infective, and one way to do that is to start infective will be this initial count infective, and here it's 200,000 minus it. So the total will be what? Between these two will be, if I sum these up, it will be what?
Total population.
It'll be, 200,000. Okay. Ladies and gentlemen, you'll notice that any logic puts dotted lines here and, between this and the value. I dragged over links to link them up, but it turns them into dotted lines to indicate it's an initial value relationship. This relationship is just determining the initial value of the stock. So that's initial count infective. That's one change I'd like you to make for this. The next change I'd like you to make is, and it's the final one till we can start exploring this, will be I'd like you to make the mean immunity duration 275 hours. I had said 270 days, and I realized I screwed up. So let's just make it 275 hours. Okay, that will allow me to demonstrate it most directly. Okay. So again, two additions. Initial count infective, hitch it up to a susceptible and infective, and subtract it off from number initially susceptible, add it to the number initially infective. Its initial value is 470. And then secondly, mean immunity duration should be 275 hours. Okay, having done that, we can go and, any questions on that? Okay, I'd like you to go to baseline, and I'd like you to make sure the count of healthcare workers is set back to its default value, just so we can have a point of reference. The default value for it is 30. So in the baseline, the kind of reference scenario, the scenario against which we'll compare other results, I'd like you to set it to 30, okay? And you'll notice that it's initially bold, which means it's a different value. But if you set it back to 30 and you kind of leave it and come back, you'll notice it's no longer indicating it has changed. It just says 30. Okay? Okay. So, ladies and gentlemen, we are going to experiment with this model. Having added this so we could have more people start infected, and having made it so that we have a mean immunity duration of 275 hours, I'd like to run the baseline. So here we are, we're going to run it, and I'm going to just run it at full tilt using this virtual time button, and we see it run out. Now what's going on here? Can anyone narrate what's going on? I would remind you that the number effective is shown in red. Can anyone give a kind of story about what's happening here? You might want to look at the value of this duration of infection too. So what's going on? What's happening at the initial start of the model? Well, let's run it in slow-mo, right? We have that option. So here we'll go run this, and I'd like you to keep track of this duration of infection. It starts as 13 hours, 14 hours. What's going on with this duration of infection for the first part of the model? Well, ladies and gentlemen, people are waiting longer and longer for treatment. It's going up and up and up. It started at 12, and now it's gone up to 930 hours, okay, with 30 healthcare workers, okay? Let's keep on going. And you see that it rises till it's remarkably high rates, and there it plateaus at very high levels. Why is it? Oh, okay. Now it's coming down. Okay, between 230. It's going down very, very slowly here. Okay, we could watch it and we can let it run full tilt, and what we'll see is it will go down to an equilibrium value of about 3,054 hours, which is a long time to wait for treatment. Wouldn't you agree? Yeah. Okay, ladies and gentlemen. This is the duration of infection. So what's going on that leads to this really high rate of infection? What's the story here? Why is this rate of infection so high? Why do we have almost everyone in the population infected?
The recovery rate is capped by the number of healthcare workers.
Good. The recovery rate is capped by the number of healthcare workers. And because there's a very limited number, what happens to the duration of infection? Well, it starts low. Why is it going up initially? Because there's a waiting line, right? People are ahead of us, and so we're waiting longer, and therefore we're infecting more people. Think about us coughing in line. Think about us infecting people at home, or we're waiting to get our appointment. And we're waiting days for our appointment, and meanwhile we're infecting lots of people, and so the infection stabilizes at very high levels. And so I like Janelle's, that was Janelle? Yes. Okay, so I'd like to build on our suggestion. So let's copy the baseline, and ladies and gentlemen, let's paste it in, and I'd like to instead create a scenario where we have initially let's make it 45 healthcare workers, okay? What do you think the impact of this will be? So we give it that name, and then we have to go change the value here, right? Count healthcare workers to 45. What do you think the impact of that is going to be? We've upped the number of healthcare workers by 50%, ladies and gentlemen. Okay, it's going to reduce the waiting time. How do you think that will yield outcomes in terms of the fraction infective?
The infected will stabilize at a lower.
Okay, it'll stabilize at a lower value. And just to remind you, with the baseline, we could go here, and it's a pretty easy math calculation, so we can do it. It's stabilized at about 182,000 infectives, right? Or something like, that's out of 200,000, right? People. So it's something like 91% of the population, 91.5% of the population. This is just about 183,000. Okay, 91.5% of the population or so. Let's go to initially 45 healthcare workers. How much do you think we brought it down? We increased the number of healthcare workers by 50%. We summoned people from all around the province to treat the afflicted in Saskatoon. So it went down to 174,000, which would be something like 87%. 50% more healthcare workers, and it went down a bit to 87%, right? Rather than just over 90%. Okay? Let's up it again. So let's do that same copy. We'll copy this initially 45, and we'll paste. Notice that I'm not going and modifying the model directly. I'm modifying the experiments. The experiments capture my scenarios. If you go and you modify the model, you could forget to change it back. Changing the experiment, these settings in the experiment doesn't modify the model. You don't have to worry about changing it back. So Instead of making it 45, I'm going to make it initially 60. Ladies and gentlemen, that's twice the number of healthcare workers is in the baseline. Do you think that will have the infection from the infection prevalence, the fraction of people that are infected from the baseline? What do you think it will do? Do you think it will have it? What do you think? Okay, why speculate? Let's let the model do the calculations for us. That's what computers are good for. Doing lots of stupid things over and over again to simulate this, right? Okay, now it's at 165,000. So we have something like 82.5% of the population now infected, with twice the number of healthcare workers. Ladies and gentlemen, we have not halved the fraction of infection. We've reduced it from just over 90% to just over 80%. Twice the number of healthcare workers. This is no nonlinear model. You still see we're going up in state space to an equilibrium value that's way up here. Lots and lots of people infected. Okay, ladies and gentlemen, let's raise the bar yet further. Let's muster everything we can. Import healthcare workers from Manitoba, from Alberta. Bring them in, fly them in from Ontario. Okay, here we go. We're going to have initially 75 healthcare workers. Okay, count initial healthcare workers. Okay. Anyone want to speculate? What's that going to bring it down to?
There's barely any more healthcare workers.
Okay. Barely any more?
Barely any more, yeah.
You mean any more left? Yeah. Okay, so here we go. Let's okay, what's going on now?
Oh my God. What was the magic number?
Let's go find out. Get something closer. So, ladies and gentlemen, what did we just see there? Parse what we just saw.
The infection was wiped out before it ever had a chance.
Okay, the infection was wiped out. Notice what the duration of infection is. I said it started at 12, but I was off. It looks like it started at 5 was the baseline, basically the time until treatment. Notice that doesn't budge. So what's going on here that's different from what we saw? Why is it that this is almost no one infected?
There's probably a number where there's cube rows, and it's somewhere between 60 and 75.
Good. Once you start to have beyond 60 and 75, you're going to start to have a number of new infections that's going to exceed the what? Recovery, right? So infective is going to go up, and that's going to lead to this be higher and higher, which will lead to slower and slower recovery, which leads to more infections. Somehow there's a magic number between these two, a critical threshold, a tipping point, ladies and gentlemen, which is going to allow the recovery rate to outpace the number of new infections and to us to stop the infection from spreading. So let's copy this again. Let's go find something closer to that magic number. Let's look at, what do you think? Let's do a binary search, right? 60 plus 75 is 135. And so half of that is something like 67, right? It's about halfway between. So let's say 67 healthcare workers. Okay? 67. Okay? And let's put that in. Okay? 67 healthcare workers. What do you think? We got something halfway down from the 82.5%? Let's run it. 67, ladies and gentlemen, we're dealing with thousands of hours of waiting time per patient and a fraction infective that's about 80.5%. Okay, big difference between 67 and 75. Let's have that difference again, right? So it's a difference of about 8, right? So we'll add 4 to it. So let's do 71. Okay? This is building on the Rowan suggestion. Okay, so let's copy it. Copy, paste, and let's try to zero in on what this is, or at least roughly. So not 67, let's make it 71 initial healthcare workers. 71, ladies and gentlemen. 71. Okay? Okay, let's build that. What do you think is going to happen now?
Yes.
Ladies and gentlemen, we snuffed it out. Somewhere between this 67 and 71 is this tipping point, this magic point where we're able to get it to never take off. The recovery rate is greater than the number of new infections. The basic reproductive constant is what? Less than 1 from the start. People aren't starting infected. Okay, so that's pretty nifty. Suppose, though, we do something a little bit tricky. We copy that 71 and we go up and paste it in. And we do 71 healthcare workers, and we say 600 initially affected. What do you think will happen now? Initially, okay, I'm not spelling very well. Initially infected. Okay? Okay, 71 healthcare workers. We're going to start with 600 initially infected. What do you think is going to happen now? Think the 71 will be enough? Okay, now we're back to square one. Now it takes off. It's very sensitive to how many people are initially infected. Why? Give me an intuition. Because if we have more people initially infected, what's going to be going on?
More people will be around, more people that are infected.
Yeah, they're going to be waiting longer. Think about the last few straggling in. They're going to be waiting a long time. They're going to be infecting lots of people. So it's not so much just the number of healthcare workers. It's the ratio between that and the number of people infected. But you see the point that there's two equilibria here. If we start with more people infected, it'll go up to, at the start, it'll go up to this equilibrium. If we start with fewer people initially infected, it will peter out. We saw that just a moment ago with 470 people. So it's sensitive, ladies and gentlemen, yes, to parameter values, but more to the point, more uniquely to this model from the ones we've seen, it's sensitive to the initial conditions, to the state of the model. And this is why I say, like Rowan pointed out, you have two different equilibria that you can go to with the same parameter values. These differ, ladies and gentlemen, only on the initial state, not with respect to, you know, the mean time that people have immunity or how quickly they get in, how quick or the number of contacts per person. Instead, just the initial state. If you start with a small enough initial state, it will peter out. It will go to a state where everyone ends up susceptible, no one infective. On the other hand, if you start too high, it'll go to the state up here, the state where you have a large number of people infected. So, ladies and gentlemen, that's a tipping point, and in terms of the state space, it will reflect kind of a line here in state space where it's in two different basins of attraction. We can think of this, and note that phrase, basins of attraction. These are like catchment areas. These are areas where like water will collect and go down to a lowest point. This is kind of the resting point here, the lowest point here. It's like this is one side of the Rockies and this is the other side. If we let a little drop of water, if we roll a marble here, it'll go down to this point. If we roll a marble on the other side, it will go to this point here. There's two different basins of attraction. We have this thing attracted to this attractor, this equilibrium point here, and it can go to this other attractor there. Now it turns out, we're not going to look at it for this example, but these attractors don't have to be points of total stasis. There's a notion of a dynamic equilibrium, which sounds bizarre, but the point is, in a dynamic equilibrium, then you actually go not to a fixed point where everything's in balance, you go to a limit cycle around it. You circle around it like a planet around a star, just sort of having a certain oscillation. And you can get those in these models as well. But the point is, here, depending on our point in state space, we can go to two different destinations. And if you think about a situation like this, they're commonplace. I mean, I would argue that in software development, you have these two different outcomes for software projects. You can have the same team, the same basic skill sets and so on, end up in a good situation or a bad one depending on managerial decision making or depending on the amount of work that's placed to them. And much of your goal as a manager of a software development team, as a lead, might be to try to nudge the situation from one basin to the other. You're trying to bring it across this divide. And just a little bit more investment may lead you to be able to bring it down here where the infection dies out altogether. Just a little bit more effort at the right time, boom, you switched it over between basins of attraction. But I'd like to highlight one other feature of this model before we get into agent-based modeling for the balance of the session. Ladies and gentlemen, I'd like to take a look at this model, and I'd like to do something we haven't done before in this class. I would like to take a look at the palette, and there's an area at the palette that's called controls, okay? Now, those of you from computer science background will recognize the controls here are referring not to control theory, but to widgets that we can add to the model, user interface controls, as we call them. Things that we can add to the model that allow a user to control elements of the model interactively. I'd like to drag in a slider to this model, and slide it will. So here we dragged in a slider, and I'd like to give it a name worthy of its function. So this is going to be called count HCW for slider. HCW standing for healthcare worker. So what did I do? I went to the palette that it says OK, and I'd like to drag in a slider. Okay? Here we go. Here's our slider. I'll frob it a bit so it's a bit larger. And I call that count healthcare worker slider. Now, the key thing I want to do here, and I'd ask you to pay attention. In this case, it's even more important than the name to our immediate goals. I'd like you to press link to, and you can actually point to what you want it, but I'm going to pick it from a drop down. I'm going to pick this thing that says count healthcare workers. Okay, so we're going to link this slider up to this parameter count healthcare workers. And that's going to allow us to frob, or perhaps more precisely tweak, the value of this parameter. Okay, ladies and gentlemen. So we are going to frob that, and I'd like you to set the value of this parameter. The minimum will be 0 as the default, and the maximum will be 300. So what do you think is going to happen as we frob this slider as the model runs? Anyone want to hazard a guess?
As we get closer to the tipping point, it will get lower, and like the percentage of people, it will get lower and lower until it gets to the tipping point where it dies out entirely.
Well, okay, so you're thinking ahead. You're thinking a few steps ahead about the dynamics. What will this slider allow me to do? What's kind of the function of this slider?
Change dynamically.
Yeah, it's going to dynamically allow me to change the parameters. Now, you may wonder, why do I want to do that? I mean, am I just having fun? Well, yeah, I am having fun, but this is not just having fun. It's not a desultory experiment. I'm actually going to use it to show an extraordinarily important phenomenon that I want you to be, with which I want you to be familiar. Okay, so I'd like you to go back to the baseline, and I remind you the baseline is 30 healthcare workers at the start. Note my comment, at the start. I'd like you to go run this model. Okay? Ladies and gentlemen, here we go, 30 healthcare workers. Now, ladies and gentlemen, we could go frob this thing and get it to go to a certain point, but I'm going to show you a better way to do this. The point is I'm going to start interfering with this, and I actually want you to run it so we can do controlled experiments. I actually want you to run it a certain distance out. And the way to do that is to actually press stop and to go up here, and you'll notice that up here in the upper left, you could actually set, by pulling this down, you can say run for a certain number of time units. And I'm going to set this to run for 250 time units, okay? You see that? Up here, okay? And what I'm going to do is I am going to go now, and you can see here I will say run for. So I pull this down, having pulled in 250, I'm going to say run for. Boom. And now it's running for that. And I could speed it up, but it will only run for 250 time units, okay? And you'll notice that it's running along till time 250. I can go switch to the model, and this is what I see, okay? 250 time units, the model has gone to this very high point of infection, okay? 250 hours in. Wow, infection spreads fast, unrealistically fast, in fact, given viral dynamics. That's okay. Okay, so ladies and gentlemen, we've run it to time 250. Now it's time to frob the slider. So I'd like you to take the slider, and I would like you to up it to 60. And you notice as I frob this and let it go, it'll actually adjust the count of healthcare workers. And it's not critical to be exactly 60. If you can get it near 60, 58 is fine. Small 60s is fine. That should be fine. I'll make it 58. And then you could do this again. You'll notice there's this little red thing here, and I'm going to run it forward 250. What do you think will happen now as we do that? Well, it's going to come down. Do you think if I keep on running it forward, it's going to disappear? No, why not?
Because you have a bunch of infected people, and the queue isn't going to...
Good. Good. Okay, so ladies and gentlemen, what was the number we needed to wipe this out before?
In between 67 and 70.
Good. Let's give it the benefit of the doubt. Let's drag it up to around 75. Here's 76. How's that? Do it a little bit above 75 if you wish to. Okay. Here we go. 76. Okay. Let's run it out. Let's watch the infection disappear. Right? What's going on? Is the infection disappearing? Is the infection disappearing? But I have 76 healthcare workers. That was enough to wipe it out. Remember that? We did this iteration. Why is it not wiping it out?
Because that wipes it out with the baseline number of infectives at 470 or whatever.
I couldn't have put it better. It wiped it out with the initial population of infected. It nipped it in the bud because that was enough healthcare workers to keep a lid on the outbreak when there were a small number of infectives. But are there a small number of infectives here? No, there's a large number. Okay, so let's up the ante. Pull out all the stops, ladies and gentlemen. Let's set it to 100 healthcare workers, more or less, okay? You don't have to worry about the exact. I'm going to set it to 98, maybe slightly over it. 100, okay, 102. Here we go. Ready? Is it wiping it out? Ladies and gentlemen, let's set it to 200. 200 healthcare workers, ladies and gentlemen. More than twice, well more than twice, what was needed to nip it in the bud earlier. Is this wiping it out? Is it wiping it out? 200 healthcare workers? Why are we seeing this?
Because the ratio is still high between the number of healthcare workers and the number of people affected.
Okay, so yes, it's true. We have many times the number of healthcare workers that were needed to initially keep a lid on it, but it's not enough because there's many times the number of infectives that we were dealing with there. Okay, 250, ladies and gentlemen. 250 people infected, just over. Is that enough to wipe it out? No. Okay, let's do 280, right? What's happened there? Sorry? That was enough. We reached, ladies and gentlemen, the tipping point. But the tipping point here, in terms of parameter values, was much higher than the tipping point if we started in the initial state. So the tipping point that was required here, somewhere around 270 healthcare workers, 280 healthcare workers, that allowed us to wipe it out. But that was many, many times what it was that was required in the initial state. Why is that? Because in the initial state, there's fewer infectives to deal with. Ladies and gentlemen, a stitch in time saves 9. If you could deal with the problem early on, head it off, you can do so with far fewer resources. 71 or so healthcare workers. If you allow the problem to grow and to get established, you're going to need many times that, right? 3 times, 4 times the number of healthcare workers or so. So wipe it out. This is an example of what's called lock-in. It's a lock-in effect. Once the system goes to an equilibrium, it's a lot harder to get it out than it is to head it off. And again, you think about this with a software project. Once it gets into a bad state, morale is down, the code base quality is really low, there's been lots of turnover, you have impatient clients who would otherwise be accommodating but have been waiting too long for delivery of product. Whether it's spread of infection or dealing with problems in software projects or dealing with competition in the commercial sphere, often, ladies and gentlemen, there's a lock-in effect where the system, what's needed to nudge the system from one of these basins of attraction to the other, to bring down a system from going to an adverse equilibrium where you have a high infection rate to instead bring it to a low one. It requires much greater effort once the system has already reached or getting close to that equilibrium than it does if you do it initially. A stitch in time will save 9. It's like if you repair that early on and prevent it from blowing up, it's much, much easier. And there's a lot of situations like that in life, where if we can head off the problem, it's just so much easier to deal with than if we have to mop up after it's already a problem. Complex systems are full of situations like this. Things get locked in. They get established in a way it's very hard to budge. And this is an example of this. 70, 75 healthcare workers required to keep a lid on the infection. If we had them from the start, 3 to 4 times that to deal with it after the fact. 3 to 4 times that to kind of clean up the mess that has been caused. Sometimes those investments realize tipping points early on for a small fraction of the price of what's required later. So if we're thinking about securing economies, if we're thinking about securing more efficiencies out of a system, being aware of the dynamics is important, especially if there's tipping points. And be aware that if there's a tipping point, there are multiple tipping points, it may be much easier to go from one basin of attraction early on than it will be later. This is lock-in effects, and it's very common in complex systems. Locked in because once it's established, it's much harder to change than early on. You think about addictions, it's a similar thing, right? If you can head off addiction to cigarettes by avoiding, using them, it's much easier than dealing with it after the fact where you've been smoking for a while and you're addicted to nicotine. Lots and lots of cases like this around. And this model is a very simple model that exhibits it. Any questions about this? Yes?
So
Jesse?
for our tipping point there, would like 280 be the tipping point for 50,000 because it starts changing at 50,000, or would it be the tipping point from the start, from the initial value?
Yeah, this is a good question. So you're saying here, after some experimentation, we were able to successfully lower the number of infectives here to the point where just upping this further to something like 280 some odd was able to lead to an extinction event in the number of people infected, right? We were able to bring this down to qualitatively change what was going on, to eliminate the infection from the population for all intents and purposes. And you're asking, was this tipping point somehow the right tipping point, you know, once the infection was established in general, or was it specific to this particular point? I would say it's specific to that. Okay, I have to be careful here. I actually think that it is a tipping point which would apply. Let's try to answer this empirically. My recollection is from analyzing the system, and there's some beautiful mathematical analyses behind this, which can be readily done. If we get it to very high levels and then we bring it up to 286, my recollection is that it will also bring it down even from this point. So I'm bringing up to 284, let's say. Here we go. Okay. Ooh, look at that. It's not okay. So either those extra 2 made all the difference, or my memory is off here. Okay, so I'm running it. Okay, and let's bring it up to, and I'm going to bring it up to 280. Okay, 290 to 290. Okay, fine. Boom. Yeah, so it does seem very sensitive around that point. It can bring it down even from this very high level here. It's enough to overcome the inertia of the system there. So 280, a little bit more, 290 to, you know, I'm trying to frob it slightly. 286, 288. Okay, fine. So it actually, it's a tipping point that is not purely contingent on that value of 50,000. It can break it down even from here. So this is the tipping point that is somewhat more fundamental, even though we introduce it later. Is that helpful, Jesse?
Yep.
Lock-in, ladies and gentlemen. A stitch in time saves 9 down the road. Okay? Questions on that? Yes?
This model seems to ignore the fact that healthcare workers could potentially get sick.
Indeed. Indeed.
Wow.
Yes, and so great segue. That's going to take us closer to where,
This model's getting complicated.
yeah, so ladies and gentlemen, let's suppose, I couldn't have asked for a better segue. I think that's why Cheryl was laughing there. Okay, ladies and gentlemen, that was not planted. Suppose we wanted to keep track here of the number of healthcare workers who are, not only of the population members, potential patients who are affected, but number of healthcare workers who are potentially infected, who are in different states. What would we need to do to this model to keep track of those?
We could just say that, you know, of the possible healthcare, like,
Mm-hmm.
of the possible healthcare workers, say we have 200,
Mm-hmm.
You know, the current number of effective healthcare workers is that 200 value minus the portion of the population which
Okay.
is infected.
So we could assume, well,
That's kind of, sorry, that's not very,
no, you're expressing actually
like
fairly
the
well.
ratio of the.
Yeah, the point is that we could, one assumption might be a starting approximation that we'll assume that healthcare workers are infected and therefore unavailable at a rate comparable to the whole population.
Yeah.
So if for the whole population, 90% of people infected, we'll assume a similar thing about healthcare workers. And how easy would that be to do here? What do we need to do that? Suppose we wanted to incorporate that. What do we need to do?
It would be pretty easy.
It would be easy. So what could you add? And where would you add it?
Well, we put in a variable the infected over susceptible, or infected over total population.
Which is called fractional prevalence.
Right.
Okay.
And then we multiply that by count healthcare workers to get the percent of healthcare workers. Sorry, we Fractional prevalence is like a percentage, right?
Yes, percentage, so like 90%. It'll be
Right.
like it'll be 0.9.
So,
say,
so if we
90%.
subtracted
Yeah.
count healthcare workers times fractional prevalence from healthcare workers,
Mm-hmm.
then we have our effective healthcare workers.
That's right. Yep. Or you could create, effective healthcare workers available, and that would be 1 minus the fractional prevalence times the number of healthcare workers, identical mathematically.
Yeah.
But it would be a little variable here. And that's a beautiful little idea. Now, that's based on an assumption, as all models are, and it might be a good first approximation. What's the what are some of the limitations of that assumption? Of that, it has the great benefit of simplicity, conceptual clarity, but what's something that smells a little bit fishy about it?
We would expect the healthcare workers to have a higher level of hygiene or something.
Yeah, well, okay, higher level of hygiene, but okay, you think about your average.
But they also work around all the infected people.
Yeah,
There's
exactly.
all
The
sorts of
healthcare
stuff.
workers are like magnets for infective people. I mean, you think about your average susceptible, they're going around and a certain number of people around them are infective. Fair enough, but you think about a healthcare worker.
They're like around.
It's like everyone, well, not everyone, but lots and lots of people around them are infected. So this mean number of infectious contacts per hour for a healthcare worker might be much higher. So suppose we wanted to actually keep track of as a separate, so it's a beautiful idea, Rowan, and I have to praise you for starting with a conceptually simple, straightforward, and clear, initial approximation. But suppose we decided that, things are different enough about healthcare workers working in an environment with tons of sick people that they need to be represented. We want to keep track of the number of them. How would we do that how would we do it in a model like this?
Would we use another set of stocks?
Yeah, we could basically take the whole copy of this, make a copy of it. So now we'd have susceptible people in the general population and susceptible healthcare workers. Effective people in the general population, effective healthcare workers. Recovered people in the general population, recovered healthcare workers. Now, would those be solitudes? Would they be independent of each other? No. The evolution of how many healthcare workers is getting affected would surely depend on the fraction, the prevalence in the other population. Probably some also on its own prevalence. And the people in the general population, would they have a high number of contacts with healthcare workers, the susceptibles in the general population? Probably not. They'd probably have very limited contact with the others. So it'd be some mixing going on between them, with healthcare workers being exposed to lots of people in the general population, but your average person in the general population being exposed to a limited number of healthcare workers. So we can represent that. We wouldn't have this nice, pretty formula over here alone, but it would end up being something like this, along with what's called a mixing matrix, which would sort of capture how many of my contacts with my own group versus this other group. And there's some beautiful mathematics behind that. But fundamentally, when we boil it down, what we're going to have here is a situation where we need to duplicate these stocks and flows for another group. Suppose we want to keep track, so put that issue aside for a moment. Suppose we want to keep track of male and female. Maybe women will have somewhat different transmission probabilities than men. They're involved in somewhat different practices in terms of being careful around others, or maybe they have more contacts with others in certain cases, or less contacts. Maybe these parameters are different, but suppose we want to distinguish men and women in this model. Putting aside the issue of healthcare workers for a moment, how would we do that? So how would we distinguish fractional prevalence among men versus among women? What do we need to do?
You just raise copy it again.
Yeah, copy it again. Make a copy of it, right? Now suppose we want to keep track of healthcare workers, male, female, and general population members, male, female. What would we need to do there? How many times would it have to be copied?
Do you copy it like
4 times. It's like all combinations of them, right? Okay, now this is starting to sound expensive. Suppose we want to, maybe we want to capture the fact that individuals who are of a certain age category, like children, are more likely to mix with other children compared to mix with, with older individuals. And maybe that really matters because certain infections concentrated in children. So there, what do we need to do? Suppose we had 17 age categories, 0 to 4, 5 to 9, 10 to 14, all the way up to 8 plus. What would we need to do there? How many times would we have to copy this model if we were just thinking about age categories? So there are 17 of them. Yeah, we need to have 17 copies of this model. And then suppose we want to take into account gender. Okay, now we're multiplying this model, not just 17 categories, 34 categories. There's a combinatorics here, ladies and gentlemen. It's not just additive. You actually have to multiply the number of categories along each dimension of heterogeneity. This is about heterogeneity. We want to divide people up into categories. And to do that, the way is by copying the model. And as you can imagine, this is somewhat unpleasant. After all, we're going to be duplicating the structure. Now, fortunately, these frameworks make it easier than that would sound. So if we go and we take a look at this, and you go look at, say, recovered, or go look at susceptible here, you'll notice that there's a thing called array here. And you don't have to do it, but I'll just point out, if we do array here, we can actually end up specifying that we want to subscript this stock by some dimension. Maybe it's age. Maybe it's age and sex. Maybe it's age, sex, and occupation. Healthcare worker or not. But basically, we can actually impose subscripts. But fundamentally, what's going on beneath the covers? It makes it easier. You specify equations in terms of subscripts. It's quite tractable and it doesn't explode visually. But what's going on beneath the surface is there's actually copies of the stocks being made for every possible category. And you have to specify mixing between those categories. So, if I'm a young child, I'll have more mixing with other kids of my similar age. So there'll be a mixing matrix across those categories. Yeah?
So are we like treating them as vectors then?
Yes.
Okay.
Yes, exactly. It's treating as a vector, or in fact as a matrix, if you're thinking about age and sex, for example. But yes, you're basically subscripting it by treating it as a vector of sorts. Okay? And so we'll have a whole bunch of susceptibles, and if you think about the spread of infection, there might be a band diagonal structure associated with, susceptible given age has contact with those a bit older and a bit younger, and so you'll have sort of a structure of the mixing matrix that exhibits sort of connectivity to nearby ages, but not to all ages as much. And you can define these elements with models like this, and in fact analyze them in terms of their equilibria, etc. But ladies and gentlemen, it starts to get awkward and challenging. Also, reasoning about this contact between infectives, or between people in the general population and the healthcare workers, can become challenging. So today, as we speak, we are going to explore a new type of modeling that's very well suited to capturing heterogeneity, that's very well suited to capturing structured contacts. Okay? And this type of modeling is called agent-based modeling. Indeed. So, ladies and gentlemen, clear the deck we will. File, close all. Do I want to save it? Yeah. Boom. I'll post it as I am wont. Incidentally, I did post this afternoon the notes from last time, the derivation, including with Xiaoyan's nice correction there. There's an extra tau placed in, which made it much more beautiful and much more reasonable in its behavior. Okay, ladies and gentlemen, we are going to explore that at a very basic level right now, and we will return to agent-based modeling next time in a big way. So, ladies and gentlemen, what I'd like you to do is to go New Model, and this will be called SD ABM comparison, side-by-side comparison, by-side comparison. We're going to build a little model which is going to allow us to compare the behavior of an agent-based model with the behavior of a system dynamics models on a side-by-side basis. Okay. Okay. So we're going to say the model time units, ladies and gentlemen, will be years. Okay. And we're going to say finish. Okay. Here we go. Okay, ladies and gentlemen. Now, I'd like to go to projects, and I would like to go and do something that's very familiar with us. We're going to create a first order delay, and we're going to do it with a certain chance per unit time of leaving, as I've used the term before, hazard rate. Okay? Here we go. So, going to main, we're going down main. Okay, and ladies and gentlemen, go to the palette, go to System Dynamics, and we're going to drag in a stock. And this is going to be a stock of susceptible, and we're going to add a stock of afflicted. Okay, people who are afflicted with some health condition, and we're going to have a flow between them. And I was not artful, but I'm going to say becoming afflicted, and as you know, I need to nicely match it up, and so I'll drag this over there till it's connected. Okay, and I'll frob these locations so that you can see them here. The number susceptible, ladies and gentlemen, will start at 10,000. 10,000. Okay, and the number afflicted will start at 0. And I want this to be a first order delay so that each year people have a probability of roughly 2% per year to go from susceptible to afflicted. So how would I do that in a principled way? Well, let's add a parameter. We're going to call it probability, or we'll call it affliction hazard. How do we like that? Affliction hazard. Okay? And it's going to be what? What value? 2% per year, so 0.02. That's rough because it compounds, but we're going to connect it up to becoming afflicted. And what else does becoming afflicted depend? Number of susceptible. If there's no susceptibles left, there ain't nobody who's going to become afflicted. Okay, becoming afflicted here. The formula for it is going to be what? Susceptible times or divided by? Times. Times indeed. A hazard rate is a chance per year, ladies and gentlemen. The units, if you have a unit of a stock, that's say persons, the unit of or the dimensions of the flow is going to be what? Dimensions per unit time. Dimensions per time. In this case, time is year, right? So it's going to be persons per year. So whatever the formula is here, we need it to be of units, persons per year. This is persons. This has got to be per year, right? And remember, it's probability per year is what this is. If we divided by it, we'd get all messed up. The flow would be of units, person divided by 1 over year, which would be person years, which doesn't make any sense. Okay, ladies and gentlemen, partly I'm telling you that because students sometimes mess that up in the exam. Okay, so what are we going to see? Well, let's go elaborate this slightly more. Let's go add a graph. Here we go, a time plot. Okay, and ladies and gentlemen, the value of this time plot here, this is going to be susceptible. So this will be stock time plot. And we're going to add in a data item that will be called susceptible. And I'll call it susceptible SD. You'll see where I'm going with this. And its value will be this dot susceptible. Okay? And initially it says display up to 100 latest samples. For our purposes, that will be fine. Okay? So what did I do? I added in a time plot. I called it stock time plot. I added in data, said value, susceptible SD, and its value is given by the value of this stock. This refers to main, and so I'm asking about the value of the susceptible stock in main. What will I see if I run this model now? Will it be a straight line down? What will it be? It will be, ladies and gentlemen, curved. Okay. Okay, let's stop it. Let's stop it at time. You know, I'm having some misgivings about those initial settings because I actually would like to see it for small numbers. Ladies and gentlemen, let's go back to that model and let's have it report it, display up to 200 latest samples, and the time window will be 200 model time units. That will let us do it for a bit longer. That will be useful. So I went up here, 200 latest samples, time window 200, and I'd like you to set, for the experiment, ladies and gentlemen, it to stop at specified time 200. So what did I just do? To go over that again, I went to the time plot. I went down to the thing that said here, data update, and I said display up to 200 latest samples. I went to scale and I set it to 200 model time units. This says how many data points to show. This says over what time window. What's the width of the time window? In this case, they happen to be the same because it's updating every year. Great. And then what did I do, ladies and gentlemen? Then I went to the experiment and I told it only run it to 200 years. Stop at specified time under model time. Are we okay with that? Ladies and gentlemen, let's run it. Let's let her rip. Okay? Here we are. So we see this most distinctly curved fashion. All right? Here we go. Good. Good, ladies and gentlemen. Okay, now we're going to do something that breaks us out of our mold. We're going to do something that will follow us through the remainder of the course. Okay? Okay, ladies and gentlemen, I would like to go to the model. Save your model. Save early, save often. It's a good principle, particularly on Linux where it crashes sometimes. Okay? I'd like you to right-click. I'd like you to say New Agent Type Person. Person with a capital P. Okay? Good. Okay? Okay. Oh. Bad things. Okay. Thought I mumble. Okay. Ladies and gentlemen, person with a capital P. We've just added, how did I do that? I went here, I did new agent type, and I declared person. Okay? I don't know why this is not recording. No. On LSD, ABM 3. Okay, here we go. Boom. And start recording. Boom. Okay, ladies and gentlemen. So we have this model here with a first order delay, affliction hazard 0.02, 10,000 people starting susceptible, 0 people afflicted. We have this susceptible times affliction hazard. And ladies and gentlemen, we have a time plot that displays it till time 200. And we set the experiment to run to time 200. Okay. Now, we've just added new agent type person. Now, here we're going to do something different. We're going to go to palette. And ladies and gentlemen, I'd like you to go down to the pictures area of the palette. And you'll notice in the pictures area, we can add in a depiction of a person. Now, I know your imaginations, for some of you, run wild when you look at the options here. Some people have a particular affinity for forklift trucks. We are going to add in, let's make it a patient. Here we go. Okay, here's a patient. We've added in a depiction of the patient. And these will actually be really useful in adding in visualization soon enough. For today, it's just going to be kind of a placeholder. Ladies and gentlemen, here we have a person represented, and we are going to go into main, back to main, ladies and gentlemen, and we are going to do something which again is unprecedented. So we've just defined a theory of personhood. The theory of personhood here is perhaps singularly simplistic. The theory of personhood simply defines the fact that person is associated with a visual representation. So now we're going to add, that's our theory of personhood, that's our theory of personness. We're going to add in a population of people by going to main, and we're going to drag in person to main, and we're going to call it population. Now, to be fair here, I could say a population of agents of size 10,000, but the software engineer in me revolts against that most unpleasant prospect. Revolt why? Because we're hard-coding a value that we may wish to change, which commonly would need change. And much of software engineering is about protecting us from the undue effects of common changes. We want to build a structure that can easily tolerate common needs changing. So we're going to drag in a parameter called initial population size. And what sort of population, what sort of type do you think this will have? Okay, so we're going to actually make it an integer. Amount is an interesting idea. I believe it's used for continuous quantities. So it's going to be an integer, and by default its value, unless we specify it, will be 10,000. And we're going to use it, ladies and gentlemen, for this population here for the initial number of agents. So the initial number of agents is going to be this dot initial population size. Okay? Secondly, we're going to go to the System Dynamics palette, and we're going to hitch it up to susceptible so that the susceptible here also begin with that same population. This dot initial population size. Perhaps you see where I'm going. Perhaps some of you anticipate already possible results. And indeed, I am bent on comparing the two. So, ladies and gentlemen, what did I do? I added in a parameter. I did it from the System Dynamics palette, but I equally could have done it from the Agent palette, which we'll be exploring with some alacrity. So this initial population size parameter has a default value of 10,000. Its type is int because it counts the number. It's a discrete quantity. The initial population of the stock is given by this value of this parameter, as is the initial population size of this population. You notice, ladies and gentlemen, for this population, this is extremely important. If you look at it when we first created it, I did not emphasize, but I did so in a neglectful fashion. This needs to be a population of agents. So when you drag this in, initially it may have looked like this after you typed the name, but you need to make it a population of agents. This needs to be selected, and then you'll be able to specify initial number of agents. Otherwise, it represents, ladies and gentlemen, just a singular agent. Okay? Okay, ladies and gentlemen. So here we have our population. I'd like you further to do one thing for this population so we can see it writ large in front of us. I'd like you to go to population, and I'd like you to go down. You'll notice I click on population, and if I go do that, I'll view there's a thing called initial location. I'd like you to click in the specified point, and I'd like you to do the following. I'd like you to say uniform. That's a draw from a uniform distribution between 0 and this dot space, and remember autocomplete is your friend, space width. For y, does anyone want to prognosticate what I'm going to put here? Space height, indeed. So ladies and gentlemen, for x, uniform, this is a draw from a continuous uniform distribution with minimum value 0. I could have said, to be more explicit, 0.0, so it's clear it's a double precision value. We could have done that, and it's to indicate it's continuous, and the maximum value is space width. Okay? So we're going to place these individuals around the space that's allotted to them. And if you go to main, you can find how wide the space is. It turns out to be 500 height, 500 width by default, but we could change it and expect this to change with it. Okay, ladies and gentlemen, build your model. Now, this model is currently complaining of an error. It says initial population size is not expected but is used, and I am looking at where that is. Okay, so let's see why that is. Okay, it looks like it's actually, let's try this. So is this in fact hitched up? It is hitched up there. So that's an interesting thing. I don't remember ever seeing that error before. I think it's asking us to put a link here between those two, which is an unusual prospect in my view. So maybe we have to put a link like this. That would be a most peculiar thing. I'm going to ignore that error, which I may do at my peril, but is not used but is expected. Okay, so is it because of this? Yes, notice this X here is not used but it is expected. Okay, sorry?
I think you need to get rid of the this.
Oh, do I really? Oh, okay, well, any logic exists with limitations. Okay, initial population size rather than this. Thank you, Janelle. Ladies and gentlemen, I'd like you to run this model. And ladies and gentlemen, what are we going to see? What lies before us? There's a lot of people there indeed. Okay, ladies and gentlemen, for the sake of our eyesight, and indeed perhaps of our sanity, let's make a copy of this. Copy, and let's paste in a new one, and let's call it population size 1,000. Okay? And its initial population size will be 1,000, ladies and gentlemen. I'd like you to run it now. And what you see now will be a more pleasant aesthetic prospect. Okay, but you could see the number here getting smaller. So we're going to, you'll notice there's some dynamics of this system dynamics model, but not a lot else going on. So I'd like to quickly, with post-haste, add in a bit of dynamics here. We're a bit behind, but we can finish it up if we're focused. I'd like you to go to population. I'd like you to go to palette, into the agent area of palette. Better yet, we could go to the state chart area of the palette here. Okay? Either one, agent or state chart. I'd like you to drag in a state chart entry point. This is going to be called health state chart. State chart entry point. I'd like you to create a state here. And this state will be called susceptible. I'd like to create another state, and this state will be called what? Afflicted. And ladies and gentlemen, I would like to create a transition betwixt them. And that transition will be named. Anyone? Becoming afflicted. Ladies and gentlemen, how did I do that? I went and I dragged in a state chart entry point and I named it health state chart. I dragged in a state called susceptible. I dragged in a state called afflicted. I then dragged in a transition, which I call becoming afflicted. This transition will occur at a specified rate per year. And guess what this rate will be given? By what will this rate be given? It's this affliction hazard. And wherein lives that? Where does that live? It lives in, yes, Maine. So, ladies and gentlemen, the rate is actually Maine dot affliction hazard. Oh, affliction hazard. Affliction hazard. Okay? Ladies and gentlemen, this is going to be a probability per unit time of this agent going from one to the other. Do you see that? So each agent here, remember, I told you, a system dynamics model is organized by state. We count the number of people in different states. An agent-based model will be organized by individuals, each of whom maintains their own state. Now, ladies and gentlemen, we're just about done. There's just 2 more elements we have to add, and it's very small. Go to main, if I may ask you to. Go to population. And I would like to go down in population to where it says statistics in population. And I'd like to press to add a data item. And it's going to be called count susceptible. This is going to be a statistic over the population, ladies and gentlemen. What sort of type of statistic will it be? A count, a sum, an average? A count indeed. Ladies and gentlemen, the count here, we're going to ask for each person in turn. It's going to be named item. You could see it by looking at this. It's called item. Each person in the population is going to be named item. We're going to ask, are they in a certain state? And what state are we going to ask, are they in? In what state are we going to ask, are they located? Susceptible indeed. And to do that, for technical reasons I'm not going to go into right now, but which will be familiar to those of you who have seen static members in Java, this will be person.susceptible. Susceptible with respect to person. Because after all, we might have susceptible deer, susceptible cattle, susceptible doctors, and in any logic, each class can have its own sort of states that have overlapping names with other classes. So this is susceptible with respect to person. So we're going to ask, are they in that state? Finally, we're going to go up. So what did I do? I went here. I scrolled down to statistics. I added a statistic, called it count susceptible. I left it as count, and I said item.instate person.susceptible. The final thing I'm going to do is you go up to this time plot, and we're going to add in one more item here that will be called susceptible, and guess what? ABM. And in order to get this, we're going to say this dot population dot count susceptible. How did it know to count the susceptibles in the population? Whence did this come?
From the value we gave it.
Yeah, we just told it how to compute in the statistic for the population the number of susceptible. All we're doing here, ladies and gentlemen, is using that. So what did I do here? I went to the time plot. I did a plus to add it in. I called it susceptible ABM, and I said this dot population, I'm referring to this, because that's the thing that holds the statistic we just added, dot count susceptible. Ladies and gentlemen, that's all. Who would like me to show what I've just done? Who would like me to dwell? Yes. Okay, which part?
Sure.
So here we added
Oh,
two.
no, okay, no, like, we're actually running.
Oh, let's run it. Yeah, I share your enthusiasm, particularly since we have 1 minute left. Okay, here we go. Ladies and gentlemen, we're going to run it. Let's run it full tilt. Ladies and gentlemen, where are the two lines?
Overlap.
They overlap, ladies and gentlemen. They're very, very close. In fact, if we went here, we went view, we could go zoom in. And you'll see here, this is the number from the ABM, and it exhibits some fluctuation, does it not? This is the number from the SD model. I'll change it one thing, ladies and gentlemen. Ladies and gentlemen, we could change one thing, which would be the nature of that transition. I won't do it here because we're out of time, but I would note this is a rate per year. We also have the opportunity to set it to be a timeout, a fixed timeout. That timeout could be drawn from a distribution, for example. So we can leave after amount of time given by drawing from a distribution, or based on a condition, based on a message that reflects interaction with other agents, or when this agent arrives at a certain location. This is the vocabulary, ladies and gentlemen, the A through Zs that we're going to be using, we're going to be learning in the next few lectures. Okay? So, ladies and gentlemen, a comparison side by side of the most simple forms of each model. Again, the system dynamics model organized by state, where each state keeps track of the number of individuals in it. The agent-based model, keeping track of individuals, and each individual is in a certain state and keeps track of their state over time. Each of those individuals could have different states. They could have different parameter values if desired, although they all shared them here. But in the simplest form, we can get very good approximations of the aggregate model on the basis of from the aggregate model of the agent-based model. But we'll see that sometimes they can diverge, and radically so. Okay, so two simplest versions here. We have a population of agents, and that population is evolving over time according to a state chart with a fixed hazard. We will expand on these building blocks next time. Thank you very much. Okay, I have one point of great regret that I must share with you. A faculty meeting was announced for my department, mandatory, in 3 minutes. So I'm going to have to reschedule today's office hours. I will do so within the next 2 days. I will have an extra set of office hours shifted from today beyond Thursday's office hours. I know some of you were hoping to meet with me, and I apologize for this. It's a point of some seriousness with what's called a collegial case involving promotion. So I have to go to it today. It was a very recent announcement, but I will send times for a new meeting probably tomorrow. Okay? So thank you very much. I apologize for having to step out now. Thank you for your patience, and I look forward to seeing you at the latest by Thursday.